Assalamu alaikum. Welcome to the next class. So, in the previous class, we discussed about some construction of the transformer. Today, we'll discuss about the transformer EMF equation and transformer operation on no load. So, this is the figure in which we have assumed transformer on no load. You can see we don't have connect any load on the secondary of the transformer. The secondary terminals are open circuited. So, we have two winding transformer on no load. When this is the case, the primary is usually connected to a sinusoidal voltage source of frequency f at the primary side, and we're assuming that resistance of the winding is zero and there will be no leakage flux. These are the assumptions for the time being. So primary has a number of turns n1, secondary has a number of turns n2, and this is the core material. And since transformer is on no load, we assume that the secondary of the transformer is open circuited. Now the primary current or the primary winding draws a small amount of alternating current of instantaneous value I0, which is called the exciting or no load current from the voltage source with positive direction as indicated on the diagram. So I'll come back to this. You can see this will be the positive direction of the current as we have assumed this to be the source. So we need to calculate the direction of this EMF and direction of this EMF. So induced EMF will has always the opposing nature. So when this is the flux that is generated by this exciting current, you can see the current direction is in this way, in this way, in this way, in this way. And when this happens, you can see that by curling the fingers along these currents, and the direction of the thumb will be the this direction of flux. So you can easily get that the direction of the flux will be like this for this current to flow. So now EMF will be induced in such a way so that the current produced by this EMF will produce the this flux which will be in downward direction, because it will try to oppose this flux to decrease this flux. So in that case, what it does, it will try to make flux in this direction, and by doing so, in this case you have to do the reverse to calculate the direction of the current by assuming flux to be on downward direction. By doing so, you will get the current direction to be opposite, like this, like this, like this, and like this. Yeah. Current direction to be this one. That means in this direction. When this happens, you will know that the current which is leaving this source, the current which is leaving the source will be the positive. That means this will be the positive terminal, this will be the negative terminal. Overall current will be in this direction because the current produced by this will be always greater than this, and the total current will be on this direction, that is from here to here. But this will be definitely very small current because it is opposed by the production of this EMF. Similarly, for this case, you can see that the flux direction is downwards in this case. Let's assume we connect some load and we'll see what will be the direction of the current. When we do so, the flux direction is downwards. I will do again the same thing. We'll curl the fingers around these turns, but we'll point the thumb in the direction of the flux that is produced by this winding, but this will produce the flux upwards to cancel out this flux. So when that happens, you will see that the current direction in this case will be like this. This will be this, this will be this, this will be this. That means current direction will be this direction, this direction, this direction, this direction. So current direction will be leaving at this point. Current will be leaving at this point. That means this will be positive, this will be negative. So this is very important to determine the current direction by knowing this, how the coil is trying to oppose the flux. Here, as I told you that we're assuming resistance to be equal to 0, you will see that this voltage, that's V1, will be equal to EMF. The exciting current establish flux phi in the core, that's positive direction, that's this direction, marked on the diagram, all of which is assumed to be confined to the core, that is, there is no leakage flux. We're assuming this flux to be confined to the core. Now the primary winding will have flux linkages. The total number of flux linkages are usually denoted by lambda. So lambda 1 is the flux linkages of the winding 1. Total flux linkage will be equal to n1 into phi. So these flux linkages will induce this EMF E1, and I have told you how to calculate the direction. Now I will calculate the actual value. So this will be equal to d lambda 1 by dt, that is d lambda is, sorry, lambda 1 is equal to n1 into phi, it will be equal to n1 d phi by dt. This is the EMF that will be induced in this winding. As per Lenz's law, the positive direction of this EMF opposes the positive current direction and is shown plus minus polarity marked on the diagram. That is, EMF will have this plus, this minus direction, as it is opposing the current flow by producing the flux in the opposite direction, and the net current will be very small. So according to the Kirchhoff law, V1 is equal to E1, as we have assumed winding resistance to be 0. If there would have been some winding resistance, there this V1 would have been greater than this E1. Thus E1 and phi must be sinusoidal of the frequency f of the same frequency, the same as that of the voltage source, because from here we are supplying some voltage, it is uh, producing some current I0, this will be also sinusoidal, and when it produces the flux, this will be sinusoidal. When sinusoidal flux is produced over here, it induces EMF, which also will be sinusoidal. So all the three will be sinusoidal in nature, and they will be having the same frequency f. Let us assume that f is equal to phi max sine of omega t. Phi max is the maximum value of the core flux, and omega is equal to 2 pi f radians per second, and f is the frequency of the voltage source. The induced EMF in the primary winding will be even, as we had just told, that it will be equal to n1 d phi by dt. So when we differentiate this phi, it will be equal to phi max, this omega, cos of omega t. So total will be equal to omega n1 phi max cos of omega t. You can see from here, this is phi will be equal to phi max sine of omega t, and E1 will be equal to this much cos of omega t. You'll see that E1 will be leading to the phi by 90 degrees, because this is cos and earlier phi max is sine omega t. I can write it as like this: omega n1 into phi max sine of omega t plus 90 degree. You can see E1 is leading to the this phi by 90 degrees. Now the RMS value of the induced EMF, this will be the maximum value of the EMF, because this E1 will be the instantaneous value of this induced EMF. This will be its maximum value. Its RMS value will be this maximum value divided by root 2. So this maximum value will be equal to 2 pi f n1 phi max. When you divide it by root 2, this 2 will be converted to root 2. It comes out to be root 2 pi f phi max. So multiplying root 2 and phi will get 4.44 f n1 phi max. This is known as EMF equation of the transformer, and this is very important equation, because from this we can calculate the value of the induced EMF. Or sometimes if this voltage is given, we can get the value of phi max. So this is an important equation and is known as EMF equation of the transformer. From this you can get phi 1 will be equal to E1. And for practical transformer, as I have told you, for this case we are assuming the resistance to be negligible, which is 0. So E1 will be equal to V1. For practical transformer, this resistance is very small, and for practical transformer also, this E1 is always taken to be equal to V1. So phi max will be equal to V1 divided by 4.44 F into N1. And from this equation, you will see that this E1 or V1 and this F, these are the properties of the input voltage source. So when we supply some voltage with some frequency, it becomes fixed. And by construction, we have already designed the transformer for certain values. You will see that N1 will be also constant by the construction. So you will see that this phi max will always be constant, and phi max will be constant. So the transformer will practically be constant flux machine, independent of other things. It will always depend upon the V1, F, and N1. It does not depend upon the load current. So whether the load current is 0, whether the load current is full load current, transformer will produce the constant flux machine. Sorry, it produces the constant flux, so that's why it is known as constant flux machine. So This usually we calculate it for the transformer. It is actually true for all other machines. For all other machines, they are also constant flux machines. But for the time being, you remember this for the transformer only. Even if the resistance of the primary winding is taken into consideration, E1 is approximately equal to V1, as I have told you just now, as the winding resistance of the transformer are extremely of small order. It is therefore seen that the maximum flux in the transformer is determined by the ratio of this and this, at which it is excited. That it depends upon the value, it depends upon the ratio of the input voltage and the input voltage frequency. We can change the flux by changing either of the two, having the difference, because N1 will be fixed by the construction. We cannot change it. Once we construct the transformer, it becomes fixed. After that, we can change the flux by changing voltage or frequency. Now, this flux is confined, all the core flux is confined to the core, and it will link the secondary coil since there is no leakage flux. When it links the secondary coil, we have an induced EMF in the secondary coil as well, that is determined by E2, which is equal to N2 d phi by dt. So the polarity of the E2 is marked plus and minus on the figure according to Lenz's law. E2 tends to cause the current flow whose flux opposes the mutual flux phi. So I have explained this in the first slide itself, that how to get the plus and minus. We just have to first select the direction of the flux which will be opposed to the main flux, and then as per that we will point the thumb in the direction of the opposing flux, and the fingers, the curling fingers, will determine the current. And at the point at which uh, the current level, we mark that point to be positive, and the point at which the current enters to the winding, we mark that point to be positive, sorry, negative. Further, it is easily seen from equation 1 and 2 that E1 and E2 are in phase, because E1 will be equal to uh, N1 d phi by dt, so E2 will be equal to N2 d phi by dt. This quantity is same, this is a pure number, so E1 and E2 will be in phase. So from these two equations, we can write E1 divided by N1 is equal to d phi by dt, and E2 divided by N2 is equal to d phi by dt. So when the right hand side for these two equations are equal, that means E1 by E2 instantaneous value will be equal to N1 by N2, it is equal to A. And for RMS values, E1 by E2 is equal to N1 by N2 is equal to A, which is the ratio of the transformer, or transformer ratio. Now, the value of the exciting current I naught has to be such that the required MMF is established so as to create the flux demanded by the applied voltage. So that means this exciting current I naught has to be uh, has to got the value which produces the required MMF in the core. So if we assume, usually when we analyze the transformer, we assume in most of the parts, we assume BH relation to be linear. If we assume such a thing, that means there is no hysteresis, no saturation. The exciting current has only magnetizing nature. That means it has only magnetizing component. It does not have any loss or something else, and is proportional to a sinusoidal flux and in phase with it. So that means the magnetizing current and flux will be in phase as is shown in this case. And even exciting current, because exciting current will now only have this magnetizing component of the current, it will not have any other component, so this magnetizing component will be in phase with this, and it will be lagging to the induced EMF by 90 degrees, as I have told you earlier. From these two equations, this E2 is equal to d phi by this E is equal to d phi by dt. Phi is sine omega t, this E2 is cos omega t, so it will be lagging. So if this is V1, this will be phi, and this Im magnetizing component of current will be in phase with it. However, the presence of hysteresis and the phenomena of the eddy currents, though of different physical nature, definitely they will not be of the same nature as that means they will not uh, lost the power in terms of heat as is done by the resistor. They are doing that in a different manner. So, but we'll take it as it is doing it in the form of a resistance. When the loss is done in the form of the resistance, that means resistance is drawing a current, and we know that the current that is drawn by the resistance will be in phase to the voltage that is applied to the resistance. So, though of different physical nature, they have different physical nature, both demand the flow of active power into the system. Because when active power flow into the system, we assume that this is because of the resistive component of the current. And as a consequence, the exciting current I naught has another component II in phase with V1. Because this II, when it is in phase with V1, this is producing the active power. Thus, the exciting current lags the induced EMF by an angle theta naught slightly less than 90 degrees. Because this is the core loss component of the current, that is II, or iron loss component of the current. It is in phase with this V1. So total exciting current will be now comprising of two components. One is the magnetizing current, another is the core loss component of the current. When we add them in the phasor form, we will get I naught. Definitely this II will be very small. You will see that this I naught will have practically value close to this Im, and this angle theta naught will be practically close to 90 degrees, but it will be slightly less than 90 degrees as shown here. You can see the variation of the flux and voltage. This flux is lagging to this voltage by 90 degrees as is shown by this phasor diagram as well. This is the same phasor diagram because I am showing this flux diagram individually for this V1 and phi, and then here phasor diagram is drawn by rotating this phasor 90 degree to the right in or clockwise direction, and then by drawing this Im and II as per the requirement, that is this will be lagging to this because Im will be in phase this phi and II will be in phase with V1. Adding them we get I naught, which is slightly which is lagging to this V1 slightly less than by 90 degrees. So this is how we have uh, determined the phasor diagram by explaining the mathematical equations. And as I told you, this is since this is the active power loss, that is the hysteresis loss and eddy current loss, we represent them. We represent almost always this active power loss by a resistive current, or we can say in phase component of the current. Now, the hysteresis which caused the current component II leading Im by 90 degree, and eddy current add more of its component, because eddy current will also have the form of the power loss. So as I have told you, power loss will be considered to be done by a current which is in phase with the voltage. So eddy current will also add some component of the current in phase with this II, so that it will be slightly increased as compared to the earlier one. So until now we are assuming that the BH curve is linear. Now the effect of saturation non-linearity is to create the family of odd harmonic component in the exciting current. So you need to remember this, and this is very important when we consider the saturation uh, in the BH curve. You'll see that there are some odd harmonic which gets introduced in its exciting current. The predominant being the third harmonic, and the predominant is the third harmonic. This may constitute as large as 35 to 40% of the exciting current. So this is the value of the third harmonic component present in the exciting current. It will be assumed here that the current Im is the magnetizing current and is responsible for production of the flux. As I told you, this Im will be in phase with this flux. While II is the core loss current responsible for the active power loss being drawn from the source to provide the hysteresis and eddy current loss, that is this II. The excitation current in a typical transformer is only up to 2 to 5%, and in some cases it may be shown as 2 to 6% of the full load current. The net current drawn by the transformer under loaded condition is almost sinusoidal, because the no load current is only 2 to 5%, and from this the third harmonic component or harmonics which is predominant, that is 35 to 40% of this, it will be very small, and when you add it to the full load current, you will see there is almost no uh, there is almost no contribution of this no load harmonic current to the full load current. So in that case, it is practically it is almost negligible. So we don't consider. But the effect of this odd harmonic and the effect of the saturation, which results in the harmonics present in the system, we will discuss it in the present this in the chapter coming ahead. So from the phasor diagram, you can see that the active power Pi will be equal to V1 into Ii or E1 into Ia, but I is equal to I naught cos of theta naught. So it will be equal to E1 I naught cos of theta naught or V1 I naught cos of theta naught. As I told you, it can be done for the practical transformer as well as for ideal transformer or this type of a transformer when we assume this resistance to be equal to 0. Now, in a practical transformer, the magnetizing current I naught, actually this should have been Im, is kept low and the core loss is restrained, that is Ii. This should be Im because I naught is the exciting current, Im is the magnetizing current, and Ii is the core loss component of the current. It is restrained to the acceptable by use of high permeability silicon steel in a laminated form. So I have told you what is high permeability, what does this do, silicon, why we add this silicon and why we use the steel and why we use the laminated core. Now from this phasor diagram, no load phasor diagram, we can determine its no load circuit. We can determine its no load circuit, we can behave similar to this phasor diagram. So the parallel circuit model of this exciting current as shown in this figure, you can see that this II uh, will be in phase with V1 because II will be equal to II will be the resistive component. It will be as it is drawn by some resistance. So II will be shown flowing to the resistance. We are modeling this II by a resistance because it is in phase with V1. Similar, this Im we are modeling it by a reactance because this reactance will be drawing current which is lagging to the voltage by 90 degrees. So this Im will be equal to Vm divided by this Xm, and this Ii will be equal to Vm V1 divided by this Ri. Where from this, since we have used GI because some parallel circuits, it will be always very easy to add the admittances. For resistance, admittance will be its conductance, and for this reactance, its admittance will be its susceptance. G is the conductance, which is equal to 1 by Ri, Gi. Bm is the susceptance of this reactance, that is equal to 1 by Xm. So I naught will be equal to Ii, phasor sum of Ii plus Im, and here we are supplying the V1, and the output of this will be E1. And since there is no resistance, you will see that this voltage and this voltage will be equal. If there is some resistance over here, definitely this voltage will be slightly higher than this voltage, but practically we are taking them to be we are taking these voltages to be equal as well. So where conductance Gi accounts for the core loss current, that is Ii, and the inductive susceptance Bm will account for the magnetizing current, that is Im, which is shown in this figure. So both these currents are drawn at induced voltage E1, which will be practically taken to be equal to V1 for a resistance or no leakage primary coil. Even otherwise also, when resistance is present, there is some leakage, E1 is taken to be equal to V1. So this is very important model of the transformer on no load, where we assume resistance to be equal to 0, that it comprises of a parallel resistance and some this reactance. This reactance actually accounts for the magnetizing current, or we can say if it accounts for the flux, and this accounts for the core losses. Now let us try some numerical on this and we will get more insight on this. A transformer on no load has a core loss of 50 watts, draws a current of 20 amperes, and has an induced EMF of 230 volts. Determine the no load power factor, core loss current, and magnetizing current. Also calculate the no load circuit parameters of the transformer. Neglect winding resistance and leakage flux. That is, we have to calculate the no load model of the transformer. So cos theta will be simply, if we know that this power, that is 50, it is equal to V, that is this I into cos of theta naught. This will be the input power. So from this, since power is given, input current is given, input voltage is given, cos theta will be equal to 50 divided by 2 into 30, that is equal to 0.108 lag. For no load, it will be lag. And you can see the amount of cos phi will be very less. If II would have been 0, this cos phi would have been equal to 0. So that is theta naught is equal to 83.76 degrees. This theta naught will be calculated from this because it's equal to cos of theta. Theta naught will be equal to cos inverse of 0.108. Now from this, II will be equal to this I naught cos of theta naught, and Im will be equal to I naught sine of theta naught. So Im will be equal to I naught sine of theta naught, that is equal to I naught is 2 sine cos inverse of this, that is equal to 83.76 degrees, that is equal to 1.988 amperes. You can see from here theta naught is very close to 90 degrees. There is hardly any difference between the magnitude of exciting current and this magnetizing component. You can see exciting current is 2 amperes and magnetizing component of the current is 1.988 amperes. So as I have told you earlier, the magnitude is very sometimes we can take this current to be equal to the exciting current as well. So core loss component will be equal to II, that is I naught cos of theta. I naught is 2, cos of theta is equal to 0.108. That comes out to be equal to 0.216 amperes. This is the value of the core loss component of the current. Now to calculate the parameters, the no load circuit model, we need to calculate GI and VM, or RI and XM. So V square GI, you can see actually this should have been V1 square divided by this RI should be equal to II, or V1 square into GI will be equal to II, sorry, equal to PI, that is the input power, because power will be drawn by this only, which is given as 50 watts. So GI into VI square is equal to PI, so GI is equal to PI by V1 square. So PI is 50 divided by 230 square, this is equal to 0.945 into 10 to the power minus 3 mho Siemens or ohm inverse. So we can get the value of Ri will be equal to 1 by Gi, that is equal to 1058.2 ohms. So this is the value of this resistance, where actually it is nothing but we are modeling the core loss by a resistance. Similarly, Im is equal to Bm into V1. This Im is equal to V1 divided by Xm, or V1 into Xm will be equal to Im. You can also get it, II will be equal to this VIGI. In that case also you will get the value of GI. So since this has been calculated from the power, usually it is calculated without calculating II. So but VM usually is, so BM is usually calculated first calculating IM. BM is equal to IM by V1, that is equal to 1.988 over 230, that is 8.64 into 10 to the power minus 3 mho Siemens or ohm inverse. And when we take the inverse of this, you will get XM is equal to 115.74. So I think this is very clear to you, and you'll be able to determine the no load circuit model for the transformer. And after this, we'll calculate it's actually the other parameters also for a practical transformer, and we'll do it in the next class. Thank you.